There is a moon orbiting Jupiter right now that erupts more violently than every volcano on Earth combined. Its surface is younger than most buildings in your city because lava buries everything within roughly 1 million years or less. Plumes of sulfur and rock blast 300 miles into space, tall enough to be seen from other worlds. But here is the part that breaks your brain. This moon is barely larger than ours. It has no plate tectonics. It has no internal engine like Earth. Something else is doing this. Something external. Something so powerful it turns an entire world inside out on a permanent basis. The answer is not deep inside Io. The answer is in its orbit. And once you understand why, you will never look at gravity the same way again. If exploring the most extreme corners of our solar system excites you, tap like and subscribe to support more adventures like this. Your support truly makes these journeys possible and means the world to me. Now, with that said, get comfortable and let's begin. In March of 1979, a young navigation engineer named Linda Morabito was sitting at her workstation at the Jet Propulsion Laboratory in Pasadena, California, performing what should have been one of the most mundane tasks in the entire Voyager mission. The Voyager 1 spacecraft had swept past Jupiter and its moons just 3 days earlier, completing a high-speed flyby that carried it through the Jovian system at roughly 17 kilometers per second. The encounter had been a triumphant success by every measure. Stunning images of Jupiter's banded atmosphere, the churning violence of the Great Red Spot, the intricate dynamics of cloud systems large enough to swallow Earth several times over, had already been transmitted back across more than 600 million kilometers of space and were making headlines around the world. But Morabito was not looking at Jupiter. She was looking at Io, the innermost of Jupiter's 4 large moons, and she was not looking at it for geological reasons. Her assignment was navigational. She needed to locate background stars near Io's disk in the Voyager photographs, so she could use their known positions to verify the spacecraft's trajectory and calculate course corrections for the next phase of the mission. It was the kind of painstaking, methodical work that keeps spacecraft on target but rarely produces surprises. She pulled up the image, a frame showing Io as a brightly lit crescent against the dark sky, and began scanning the region just off the moon's illuminated edge for stellar reference points. That was when she noticed something extending off the limb of the moon that had no right to be there. A bright, crescent-shaped feature arced upward from the edge of Io's disk, rising far above the surface and curving outward into the emptiness of space. It was enormous. It was luminous. It was structured in a way that immediately ruled out image noise or random processing artifact. At first, Morabito considered the possibility that she was seeing another of Jupiter's many small moons emerging from behind Io, its sunlit surface peeking into view. She checked the orbital geometry of every known Jovian satellite against the timing and pointing of the image. None of them matched. The feature was not a moon. She then considered whether the bright arc could be a technical artifact, some glitch introduced during the transmission of image data across the vast distance between Jupiter and Earth, or perhaps a defect in the photographic processing chain. She examined other frames taken at nearby times with different exposure settings. The feature persisted, consistent in shape and position relative to Io's surface. The artifact explanation collapsed. What remained was the explanation that seemed, at first consideration, the least plausible of all. Morabito was looking at an active volcanic eruption on the surface of Io, and the plume from that eruption was so colossal that it extended hundreds of kilometers above the moon's surface, tall enough and bright enough to be visible against the blackness of space from a spacecraft that had already passed millions of kilometers beyond the Jupiter system. Within hours of Morabito bringing the anomaly to the attention of the imaging team, the Voyager scientists redirected their focus to every frame in the dataset that included Io. The results did not reveal a single anomalous eruption. They revealed a catastrophe of volcanic activity spanning the entire globe. At least 9 separate volcanic eruptions were identified as simultaneously active across Io's surface. Enormous plumes rose from multiple locations. Dark, fresh-looking deposits of what appeared to be recently solidified lava surrounded active vents. The spacecraft's infrared instruments registered elevated temperatures at numerous points scattered across the terrain. This was not a moon experiencing an isolated geological event, a single volcano blowing its top in an otherwise quiet landscape. This was a world erupting from every direction at once, its surface alive with volcanic violence at a scale and intensity that had absolutely no precedent in the history of planetary exploration. Io was not just volcanically active, it was the most volcanically active body anyone had ever observed, and no one, with one extraordinary exception, had seen it coming. That exception constitutes one of the most remarkable coincidences in the history of modern science. Just 3 days before Voyager 1 made its closest approach to Io, a paper appeared in the journal Science authored by 3 researchers, Stanton Peele of the University of California, Santa Barbara, Patrick Casson of NASA's Ames Research Center, and Ray Reynolds, also of Ames. The 3 scientists had been studying the gravitational dynamics of the Jovian satellite system, and their calculations had led them to a striking conclusion. Io, they determined, should be experiencing intense internal heating caused by tidal forces from Jupiter's gravity, forces that were being sustained and amplified by the specific orbital relationship between Io and its neighbouring moons Europa and Ganymede. By modelling the cyclic gravitational stresses that Io's slightly non-circular orbit would produce as the moon swung closer to and farther from Jupiter on each revolution, Peele, Casson, and Reynolds calculated that enormous quantities of frictional heat should be accumulating inside the moon, potentially enough to maintain widespread melting of the interior. Their paper concluded with a sentence that many colleagues at the time regarded as remarkably bold. Consequences of this dissipation include a maintaining of the interior in a largely molten state and widespread and recurrent surface volcanism. It was a prediction, grounded in rigorous mathematics, conclusion that contradicted everything the planetary science community believed about small, cold, ancient moons. 72 hours later, Voyager proved them spectacularly, undeniably correct. A theoretical prediction made with pencil and paper was validated by a spacecraft flying past a moon more than 600 million kilometers from the desk where the calculations were performed. It remains one of the finest examples of theoretical physics and observational discovery converging in the same breath. Every subsequent mission to the Jupiter system has confirmed that what Voyager discovered was not a fleeting episode, but Io's permanent state of being. The Galileo orbiter, which arrived at Jupiter in December of 1995 and operated within the Jovian system until September of 2003, observed Io on dozens of occasions spanning nearly 8 years. Its suite of instruments, including cameras, infrared spectrometers, and magnetometers, built the most comprehensive portrait of Io's volcanism ever assembled. Galileo catalogued more than 150 distinct active volcanic centers distributed across the surface. Some of these were persistent features, erupting without interruption for the entire duration of the mission, year after year after year. Others were transient, flaring with sudden violence for periods of weeks or months before subsiding into apparent dormancy, only to reignite at the same site or at new vents nearby. The spacecraft witnessed eruptions in progress, catching fountains of lava and expanding plume canopies in real time. It measured heat flow from volcanic regions so intense that the infrared detectors occasionally saturated, overwhelmed by the sheer thermal output of a single volcanic center. The New Horizons spacecraft, which passed through the Jupiter system in late February of 2007 on its long trajectory toward Pluto, provided another snapshot of Io in full eruption. Its cameras captured a spectacular image of a massive plume rising from a volcanic center called Tavashtar near Io's North Pole. The plume extended approximately 330 kilometers above the surface, spreading into a broad, umbrella-shaped canopy of gas and fine particulates that was clearly visible against the black backdrop of space. The eruption at Tvashtar was among the most energetic ever directly imaged on Io, and it demonstrated that the volcanic intensity observed by Voyager and Galileo was not diminishing with time. The Juno spacecraft, which has been orbiting Jupiter since 2016 and continues to operate as of recent years, has obtained close infrared images of Io, revealing dozens of glowing hotspots scattered across the Moon's nightside hemisphere. These hotspots shine in the infrared like embers on a darkened hearth, each one marking a site where molten rock lies at or very near the surface. The fundamental picture has not changed across more than 4 decades of observation spanning 5 separate spacecraft encounters. Io does not go through volcanic phases. It does not experience active epochs followed by periods of quiet recovery. This is simply what Io is, a world in a permanent state of eruption, and it has been this way for as long as we have had the instruments to watch. The individual eruptions on Io operate at scales that annihilate every terrestrial comparison. The largest volcanic plumes observed on the Moon reach heights of 300 to 500 kilometers above the surface. Some observations have suggested plume heights that may approach or even exceed 500 kilometers during the most powerful outbursts. To anchor these numbers in human experience, consider the most powerful volcanic eruption that has occurred on Earth in living memory. The 1991 explosion of Mount Pinatubo in the Philippines was, by any earthly standard, a catastrophe. It ejected roughly 10 cubic kilometers of material. Its eruption column pierced the stratosphere, reaching an altitude of approximately 35 kilometers. The sulfur dioxide it injected into the upper atmosphere formed a global aerosol layer that lowered average surface temperatures across the planet by roughly 0.5 degrees Celsius for nearly 2 years afterward. It disrupted commercial aviation across the Pacific Basin. It buried surrounding communities under meters of volcanic ash mixed with rainwater into devastating lahars. It was classified as a Volcanic Explosivity Index 6 event, placing it among the most powerful eruptions in the past century. On Io, volcanic plumes routinely reach heights 10 times greater than Pinatubo's eruption column. These are not century-defining catastrophes. They are not geological emergencies. They are the unremarkable background activity of a world where volcanic violence is as constant as the ticking of a clock. If eruptions of Pinatubo's magnitude occurred on Io, they would barely register against the ambient volcanic chaos. They would be lost in the noise. The temperatures of the lavas erupting on Io pushed the Galileo science team into territory that challenged their expectations of what should be physically possible on a modern solar system body. The spacecraft carried a near-infrared mapping spectrometer, capable of estimating surface temperatures by analyzing the wavelength distribution of infrared radiation emitted by hot features. Multiple volcanic hotspots on Io returned temperature estimates exceeding 1,600 degrees Celsius. Several individual measurements pointed to localized temperatures that may have approached 1,800 degrees. Though these extreme readings remain subjects of active scientific debate because of the inherent uncertainties in remote temperature measurement at interplanetary distances, for comparison, the basaltic lavas that erupt on Earth today, the lavas of Hawaii, of Iceland, of the mid-ocean ridges, typically have eruption temperatures in the range of 1,000 to 1,200 degrees Celsius. The hottest commonly measured terrestrial lava, from Kilauea in Hawaii, emerges at roughly 1,150 degrees. The temperatures measured on Io exceed the hottest modern Earth lavas by 400 to 600 degrees, a gap so large that it implies fundamentally different magma compositions. Specifically, temperatures in the range of 1,600 degrees and above suggest ultramafic lavas, magmas extremely rich in magnesium and iron, similar to a class of volcanic rock called komatiite. Komatiites have not erupted on Earth for more than 2.5 billion years. They are relics of the Archean Eon, a time when Earth's mantle retained substantially more primordial heat and could generate the extreme temperatures required to produce these primitive, low-viscosity magmas. Io is producing lavas today that our own planet's interior stopped being hot enough to make before the first complex multicellular life evolved on Earth. On a world of any size, this would be a striking finding. On a moon that is smaller than our own, orbiting in the cold outer reaches of the solar system more than 5 times farther from the Sun than Earth, it is profoundly difficult to explain through any conventional geological process. The surface of Io records the cumulative weight of this relentless volcanic bombardment in what may be the most dramatic geological testimony available anywhere in the solar system. On virtually every solid body we have studied, impact craters function as the fundamental chronometer of geological history. The Moon is saturated with them, its ancient highlands preserving a cratering record that reaches back more than 4 billion years to the period of late heavy bombardment. Mercury carries the scars of similar ancient impacts etched permanently into its surface. Mars retains colossal impact basins like Hellas Planitia, more than 2,000 kilometers across, that date to the very earliest chapters of solar system formation. Even the icy satellites of the outer planets, worlds like Callisto and Rhea and Mimas, preserve heavily cratered surfaces that speak to billions of years of accumulated bombardment history. Craters are the default condition of old, geologically inactive surfaces. They accumulate over time and persist indefinitely, unless some active process erases them. Io has virtually none. Not a scattering of ancient craters partially buried by later volcanic flows. Not a handful of degraded remnants visible in the oldest terrains. Essentially 0 confirmed impact craters survive on the surface. The rate of volcanic resurfacing is so ferociously high that any crater produced by an asteroid or comet impact is buried beneath fresh lava flows, volcanic ash deposits, and sulfurous fallout before it can persist long enough to be recorded. The best estimates suggest that Io's surface is being repaved at an average rate of roughly 1 centimeter per year when integrated across the entire globe, with substantially higher rates in the most volcanically active regions. Over geological timescales, even modest ones, this resurfacing rate erases all evidence of prior surface history. The current best estimates place the average age of Io's visible surface at approximately 1 million years, and some analyses suggest it could be considerably younger than that. Every feature visible in every image ever taken of Io was created within a geological eye blink of the present moment. Every mountain, every lava flow, every coloured plain, every caldera rim that appears in our photographs was formed in the recent past. Everything that existed before has been buried, entombed, overwritten and erased by the ceaseless volcanic machine that operates without pause across the entire globe. The colours of that surface are as extraordinary as the processes that create them. Images returned by Voyager, Galileo, New Horizons, and Juno reveal a world painted in a riotous palette of yellows, oranges, whites, reds, greens, blacks, and browns. The dominant yellow and white plains that cover much of the surface are composed of sulfur and sulfur dioxide frost, deposited across vast areas by the fallout from volcanic plumes. Sulfur is a chemical chameleon, capable of producing a surprisingly wide range of colours depending on its molecular allotrope, its thermal history, and the rate at which it transitioned from gas or liquid to solid form. Pure sulfur at room temperature is bright lemon yellow. Heated sulfur darkens through orange to deep red, and eventually to a dark brownish black before melting. When sulfur vapour condenses rapidly, it can form metastable red or orange allotropes that persist on surfaces for extended periods. The result is that Io's sulfur-coated plains shift colour from region to region, reflecting the varied volcanic and thermal conditions that deposited them. The dark patches interrupting this sulphurous canvas are fresh silicate lava flows, basaltic or ultramafic rock erupted recently enough that it has not yet been blanketed by the ongoing precipitation of sulphurous fallout from nearby or distant plumes. Some of these dark flows extend for hundreds of kilometres, cutting across the yellow terrain like black rivers through a painted landscape. The overall effect is a world of jarring, almost aggressive colour, so visually chaotic that scientists have resorted, only half-jokingly, to comparing Io's appearance to a cosmic pizza. The analogy lacks scientific gravitas but captures the splotchy, multicoloured, seemingly random visual reality with disarming accuracy. The total thermal energy output of Io's volcanism provides what may be the single most damning number in the entire case against conventional geological explanation. Io radiates approximately 100 trillion watts of heat generated internally through its surface. This estimate derives from integrating infrared observations of the Moon's volcanic hotspots, active flows, and background thermal emission across the entire globe. Using data gathered primarily by the Galileo spacecraft and supplemented by ground-based telescopic observations and Juno measurements, 100 trillion watts is a staggering figure for any world, but it becomes truly extraordinary when compared to Earth, our planet, with all of its mid-ocean ridges spreading continuously around the globe, all of its subduction zone volcanoes actively erupting along the Pacific Ring of Fire and the Mediterranean and the Indonesian archipelago, all of its mantle plume hotspots like Hawaii and Iceland and Yellowstone, all of its geothermal fields venting heat from shallow magma chambers, its churning molten outer core, driving a global magnetic dynamo through vigorous convection, produces a total internal heat flow of roughly 44 trillion watts. Io produces more than twice that figure from a body with roughly 1/12 the surface area. Measured as heat flux per unit of surface area, the comparison that truly captures geological intensity, Io surpasses Earth by a factor of roughly 25 to 30. Earth is a world 67 times more massive than Io. Its diameter is roughly 3.5 times greater. It possesses an active tectonic system unmatched by any other terrestrial planet. It is, by every reasonable metric, the most geologically vigorous planet in the inner solar system. And this moon, this body barely larger than our own, radiates more total geological heat and does so from a fraction of the surface area. That single comparison demolishes every attempt to explain Io's volcanism through conventional internal mechanisms and demands an entirely different kind of answer. And so the puzzle arrives at its sharpest point. Begin from the most basic physical principles and ask what should be happening inside a body like Io. Small, rocky worlds cool faster than large ones. This is not a conjecture. It is a direct, unavoidable consequence of thermodynamics. The rate at which a body loses heat by radiating it into space is proportional to its surface area. The total thermal energy stored inside it is proportional to its volume. For a sphere, volume grows with the cube of the radius, while surface area grows only with the square. As a body becomes smaller, the ratio of surface area to volume increases, meaning it bleeds heat into space more rapidly relative to the energy it retains. A thimble of hot coffee cools in seconds. A bathtub of the same coffee stays warm for hours. A lake takes days. Earth's moon, which is almost exactly the same size as Io and composed of broadly similar rocky material, lost its internal heat billions of years ago. The last significant volcanic eruptions on the moon occurred at minimum around 1 billion years ago, and the vast majority of lunar volcanic activity ended far earlier. Mars, a planet substantially larger than either the Moon or Io, shows no convincing evidence of volcanic activity within the past several 100 million years. If the size and composition of a rocky body were the sole determinants of its geological lifespan, Io should have gone cold and silent long before the first fish crawled onto land on Earth. There is one internal heat source that operates in all rocky bodies regardless of their size or age. Radioactive isotopes of uranium, thorium, and potassium are naturally distributed throughout the silicate minerals that make up rocky planetary interiors. These unstable isotopes decay over billions of years, and each decay event releases a small quantity of energy as heat. In a body as large as Earth, the cumulative radiogenic heat production from trillions upon trillions of decaying atoms is substantial, amounting to roughly 20 trillion watts, enough to keep the mantle convecting, the plates moving, and the volcanoes erupting after 4.5 billion years. This is the slow-burning furnace that keeps our planet alive. But radiogenic heat production depends directly on the mass of rock containing those radioactive elements. Io has approximately 1.5% of Earth's mass. its total inventory of radioactive material, and therefore its total radiogenic heat output, is correspondingly tiny. When planetary scientists calculate the expected radiogenic thermal output for a body of Io's mass and estimated composition, the figure comes to no more than 5 to 10% of the heat flux actually observed escaping from Io's surface. Radioactive decay is real. It contributes measurably to Io's thermal budget, but it falls short of explaining the observed output by roughly an order of magnitude. More than 90% of the energy powering Io's volcanic fury has no nuclear or chemical source within the Moon itself. It must be arriving from outside. On Earth, the path from internal heat to surface volcanism runs through a well-understood chain of processes. Internal heat drives slow convective circulation within the mantle, where hotter, less dense rock rises and cooler, denser rock sinks over millions of years. This convection exerts forces on the rigid outer shell of the planet, the lithosphere, which is fractured into a mosaic of tectonic plates. Where plates diverge at mid-ocean ridges, mantle rock ascends to fill the gap, decompresses, partially melts, and erupts as basaltic lava, creating new oceanic crust. Where plates converge at subduction zones, one plate descends beneath the other into the mantle, carrying water-bearing minerals down with it. That water lowers the melting point of the overlying mantle wedge, generating magmas that rise to feed chains of explosive arc volcanoes like those of the Andes, the Cascades, and Japan. Where deep-seated plumes of anomalously hot mantle material rise from near the core mantle boundary, they impinge on the base of the lithosphere and punch through, creating intraplate volcanic hotspots like Hawaii, Iceland, and Yellowstone. Every major volcanic province on Earth connects to one of these three mechanisms, and all three trace their energy ultimately back to the internal heat of the planet. Plate tectonics is the master framework through which Earth organizes and releases its thermal energy at the surface. Io has absolutely nothing resembling this framework. There are no plate boundaries anywhere on its surface. There are no linear spreading ridges where new crust forms. There are no arcuate subduction trenches where old crust descends into the interior. There are no transform faults where plates grind laterally past one another. There are no systematic chains of volcanoes arranged in the geometric patterns that plate interactions produce on Earth. The more than 150 active volcanic centers identified on Io are distributed across the surface in an apparently disordered fashion, erupting wherever subsurface magma can find or force a conduit through the overlying crust. The pattern is not organized, it is not systematic. It is chaotic, globalized, omnidirectional. This distribution is flatly incompatible with any form of plate tectonic activity. Whatever is powering Io's volcanism, it is not doing so by moving plates and concentrating volcanic output along their boundaries. Instead, the heat appears to be entering the interior everywhere at once, uniformly, globally, producing magma throughout the mantle that then rises through whatever random pathways are available. Consider the complete accounting of possible explanations, laid out one by one. Primordial heat, the thermal energy inherited from the Moon's formation 4.5 billion years ago, depleted long ago in a body this small, entirely inadequate to sustain current activity levels. Radiogenic heating from the decay of uranium, thorium, and potassium in the interior, present and contributing, but capable of explaining at most 10% of the observed thermal output, leaving 90% or more unaccounted for. Plate tectonics driven by mantle convection, completely absent, with no surface evidence of any organized tectonic system, no plate boundaries, no spreading centers, no subduction zones, no transform faults. Mantle plume volcanism driven by deep internal thermal anomalies, conceivable as a mechanism for transporting heat to the surface. But a plume requires a source of anomalous heat at depth, and no known internal process can generate the required temperatures in a body this small with this little radiogenic fuel. Every single mechanism that planetary scientists have spent decades developing and refining to explain volcanism on the terrestrial planets fails when applied to Io. Not by a narrow margin that could be closed with better measurements or slightly adjusted models, by a factor of 10 or more. The energy budget is broken. The known internal sources cannot come close to matching the observed output. The heat powering the most volcanically active body in the solar system is not being generated inside that body. It must be arriving from an external source. And the identity of that external source is not hidden. It is not subtle. It is not buried in some obscure orbital parameter or detectable only through advanced mathematical modeling. It is hanging in Io's sky, visible from every point on the surface, dominating the heavens with a disk that spans roughly 40 times the angular width of the full moon as seen from Earth's surface. Jupiter, the largest planet in the solar system, a gas giant containing more mass than all the other planets, moons, asteroids and comets in the solar system combined. A world with 317.8 times the mass of Earth and a gravitational field so immense that it shapes the orbital dynamics of everything within tens of millions of kilometers. Io orbits this colossus at a mean distance of just 421,700 kilometers, the closest of all 4 large Galilean moons, sitting deep inside Jupiter's gravitational well, closer to the giant planet than any comparably sized natural satellite in the solar system comes to its parent body. At that distance, the tidal forces Jupiter exerts on Io are not a minor perturbation. They are not a subtle astronomical influence that slightly adjusts the moon's shape or orbital evolution. They are a relentless, crushing mechanical deformation of the entire solid body of the moon, repeated on every single orbit, every 42.5 hours, without cessation for billions of years. But stating that Jupiter's gravity deforms Io does not, by itself, explain the heat. A constant deformation does not generate energy. If Io were permanently stretched into a fixed shape by Jupiter's tidal pull and simply stayed that way, no heat would be produced. For tidal forces to generate the kind of thermal energy we observe, the deformation must change. The tidal bulge must grow and shrink, shift and oscillate, flex and relax in a repeating cycle. That requires Io's orbit to deviate from a perfect circle. It requires eccentricity, and maintaining that eccentricity against the very tidal forces that constantly work to erase it requires a mechanism of extraordinary gravitational precision involving not just Jupiter and Io, but 2 other moons locked into an orbital relationship so exact that it has functioned as an energy pump for billions of years. How this pump works, how it converts the serene mathematics of orbital mechanics into the volcanic hellscape we observe on Io's surface, is a story that transforms a seemingly impossible anomaly into an inevitable consequence of physics. Everything we have catalogued so far, the plumes, the lava lakes, the impossible temperatures, the erasure of craters, the energy output that shames an entire planet, all of it traces back to a single cause. And that cause is not hidden inside Io. It is written in the geometry of its orbit. Understanding that geometry is the next step, and it changes everything. Start with something you already know. Stand on any ocean shoreline on Earth and wait for 6 hours. The water will rise. Wait another 6 hours. The water will fall. This rhythm has repeated itself every single day for as long as oceans have existed on this planet. So reliably that ancient civilizations built their fishing schedules, their naval campaigns, and their mythologies around it. The tides are so familiar, so woven into the texture of coastal life, that most people never pause to consider the extraordinary physics behind them. But the mechanism driving ocean tides on Earth is the same mechanism, scaled up to a degree that beggars imagination, that is tearing Io apart from the outside. Understanding tides on Earth is the first step toward understanding why a moon, smaller than our own, is the most volcanically active body in the solar system. Ocean tides exist because gravity does not pull equally on all parts of a large object. The moon orbits Earth at a distance of roughly 384,000 kilometers. Its gravitational pull reaches across that distance and acts on every particle of matter in our planet. But gravity weakens with distance, according to an inverse square law. The side of Earth facing the Moon is approximately 12,700 kilometers closer to the Moon than the side facing away. That difference matters. The near side of Earth feels a slightly stronger gravitational tug toward the Moon than the center of Earth does, and the center feels a slightly stronger tug than the far side. This variation in gravitational pull across the body of the planet is called the tidal force. It does not pull the Earth uniformly toward the Moon. It stretches Earth along the line connecting the two bodies, creating a slight elongation, a bulge on the near side where material is pulled toward the Moon, and a corresponding bulge on the far side where material is effectively left behind as the center of Earth is pulled more strongly than the far surface. In the ocean, these bulges manifest as two high tides on opposite sides of the planet. As Earth rotates beneath these bulges, any given coastline passes through two high tides and two low tides approximately every 24 hours and 50 minutes. The amplitude of these ocean tides varies depending on coastal geometry, water depth, and the alignment of the Moon and Sun. But typical open ocean tidal bulges measure roughly a meter or so in height. Along certain coastlines where geography funnels the tidal flow, the range can reach 10 meters or more, producing dramatic tidal bores and vast expanses of alternately submerged and exposed seabed. What most people do not realize is that the solid body of Earth also deforms under tidal forces. The rock beneath your feet is not perfectly rigid. It has some elasticity, some capacity to flex under sustained applied force. Twice each day, the solid Earth bulges very slightly toward the Moon and relaxes again as the geometry changes. The amplitude of this solid body tide is approximately 30 to 40 centimeters. The ground you are standing on right now is gently rising and falling by roughly the height of a shoebox on a 12-hour cycle, and you cannot feel it happening because the deformation is so smooth, so gradual, and so uniform across your local area that no human sense can detect it. This solid body tidal flexing on Earth is real and measurable, with sensitive instruments, but it is tiny. It generates a negligible amount of frictional heat inside our planet. The energy involved is vanishingly small compared to Earth's internal heat budget. The tidal deformation of Earth by the Moon is a footnote in terrestrial geophysics, interesting in principle, but insignificant in practice. Now take that same physical mechanism and change two numbers. Replace the Moon with Jupiter, and put the body being deformed not at 384,000 kilometers from the Moon, but at 422,000 kilometers from a planet that is 25,000 times more massive than the Moon. The tidal force depends on the mass of the body exerting the pull and on the inverse cube of the distance between the two bodies, the cube, not the square. This cubic dependence means that tidal forces are extraordinarily sensitive to distance. Moving twice as close to a massive body increases the tidal force by a factor of 8. Moving 3 times closer increases it by a factor of 27. Io orbits Jupiter at a distance broadly similar to the Earth-Moon separation, but Jupiter has roughly 25,000 times the Moon's mass. The tidal force Jupiter exerts on Io is therefore thousands of times stronger than the tidal force the Moon exerts on Earth. The numbers shift from centimeters to tens of meters. The solid rock of Io, its crust and mantle, physically bulges toward Jupiter by as much as 100 meters on the near side. 100 meters. That is not a subtle flexing of the ground. That is a deformation tall enough to swallow a 30-story building. The entire body of Io is being elongated toward Jupiter by a distance comparable to the length of a football field, and this deformation is happening not to water sloshing around on a surface, but to solid silicate rock under colossal compressive and tensile stress. But here is the critical point that separates tidal deformation from tidal heating. If Io's orbit around Jupiter were a perfect circle, this enormous bulge would be permanent. Io would settle into an elongated equilibrium shape, the bulge would point steadily at Jupiter, and once the deformation stabilized, nothing further would happen. A constant deformation does not generate friction. If you bend a metal bar and hold it in the bent position, the bar heats up during the bending. But once it is motionless in its new shape, no additional heat is produced. For continuous heating, you need continuous flexing. You need the deformation to change cyclically, growing and shrinking, shifting and oscillating, over and over. And for that, you need Io's distance from Jupiter to change on every orbit. You need the orbit to be eccentric. Io's orbit around Jupiter is not a perfect circle. It is slightly elliptical, with an orbital eccentricity of approximately 0.004. That number sounds minuscule. It means Io's orbit deviates from perfect circularity by less than 0.5%. In everyday terms, if you drew Io's orbit on a sheet of paper at a reasonable scale, you would not be able to distinguish it from a circle by eye. But that tiny eccentricity has consequences that are nothing short of violent. Because the orbit is slightly elliptical, Io's distance from Jupiter changes continuously as it moves along its orbital path. At the point of closest approach, called perigove, Io swings approximately 1,800 kilometers closer to Jupiter than its average orbital distance. At the point of greatest distance, called apogee, it swings roughly the same amount farther away. This variation in distance produces a corresponding variation in the tidal force Jupiter exerts on Io. When Io is closer, the tidal pull is stronger, the bulge grows larger, the moon is stretched more. When Io is farther, the tidal pull weakens, the bulge shrinks, the moon relaxes slightly. This cycle repeats on every single orbit. Io completes one orbit in approximately 1.77 Earth days, or roughly 42.5 hours. So every 42.5 hours, Io's solid interior goes through a full cycle of enhanced stretching followed by partial relaxation, followed by enhanced stretching again. The tidal bulge does not maintain a fixed size. It oscillates, it pulses, it flexes the entire interior of the moon in a rhythmic compression and release cycle that has been repeating without pause for billions of years. There is an additional subtlety that amplifies the effect. Because Io's orbit is elliptical, the moon does not move at a constant speed around Jupiter. It moves faster when it is closer to Jupiter and slower when it is farther away, following Kepler's second law of planetary motion. But Io's rotation rate is constant, locked into synchronous rotation so that it always shows the same face to Jupiter, just as our moon always shows the same face to Earth. This mismatch between the varying orbital speed and the constant rotation speed means that the tidal bulge does not point exactly at Jupiter at all times during the orbit. It rocks slightly back and forth, leading or trailing the direct Jupiter-facing direction depending on where Io is in its elliptical path. This librational rocking adds a lateral component to the tidal flexing. The bulge does not just grow and shrink, it also shifts position slightly, migrating across Io's interior in a complex pattern of three-dimensional deformation that maximizes the amount of internal friction generated on each orbital cycle. The interior of Io responds to this cyclic stress not as a perfectly rigid solid and not as a freely flowing liquid, but as something in between. Geophysicists describe this behavior as viscoelastic. A viscoelastic material deforms under applied stress, but it does so with internal resistance, and it does not snap back to its original shape instantaneously when the stress is removed. There is a time lag, a delay between the application of force and the full deformation response, and another delay between the removal of force and the full recovery. During these lags, energy is dissipated as heat within the material through a process called viscoelastic dissipation. At the molecular and microstructural level, what is happening is that the cyclic tidal stresses cause grain boundaries within the rock to slide against each other, microscopic fractures to open and close, crystal lattice defects to migrate, and parcels of partially molten rock to shift and redistribute. All of these processes involve friction, and friction converts the mechanical energy of deformation into thermal energy. Every flex of Io's interior, every pulse of the tidal bulge, every oscillation of the elongated shape converts a portion of the orbital kinetic energy of the Io-Jupiter system into heat deposited directly inside Io's mantle. The amount of heat generated by this process depends on a combination of factors that scientists have modeled extensively since the original Peel, Casson, and Reynolds prediction. The strength of the tidal forcing, set by Jupiter's mass and Io's orbital distance, determines the magnitude of the stress applied. The orbital eccentricity determines how much the tidal stress varies from one part of the orbit to another, controlling the amplitude of the flexing cycle. The internal structure of Io, specifically the rheological properties of its mantle, meaning its rigidity, its viscosity, and how these properties depend on temperature and pressure, determines how efficiently the cyclic deformation is converted into heat, and the orbital period determines how frequently the flexing cycle repeats. Together, these parameters yield a tidal heat production rate that matches, within the uncertainties of current models and observations, the approximately 100 trillion watts of thermal energy observed escaping from Io's surface. The numbers work. The theory predicts the observation. Tidal heating, driven by Jupiter's gravity acting on Io's eccentric orbit, is sufficient to explain the entirety of Io's staggering volcanic output. Let me now trace the full chain reaction from orbital mechanics to surface eruption, because seeing every link in the chain at once reveals the elegant brutality of this system. It begins with eccentricity. Io's orbit is not a perfect circle. Its distance from Jupiter varies by several thousand kilometers on every 42.5-hour orbital revolution. This varying distance produces varying tidal forces. When Io swings closer to Jupiter, the gravitational differential across its body intensifies, and the tidal bulge swells. When Io recedes to the far point of its orbit, the differential weakens and the bulge subsides. This variation produces cyclic flexing of Io's entire solid interior, a rhythmic squeezing and releasing that penetrates deep into the mantle. The cyclic flexing generates internal friction through viscoelastic dissipation. Rock grain boundaries slide, microfractures pulse open and shut, and partially molten zones within the mantle shift and deform, all of which convert mechanical work into heat. The heat accumulates, raising mantle temperatures far above what radiogenic decay alone could sustain, and driving extensive partial melting of the silicate interior. Models suggest that a significant fraction of Io's mantle, perhaps 20% or more by volume, may exist in a partially molten state at any given time, forming what some researchers describe as an underground magma ocean, or at minimum a pervasive network of interconnected melt zones. This magma, being less dense than the surrounding solid rock, migrates upward through the crust under buoyancy forces, exploiting fractures, weaknesses, and pre-existing volcanic conduits. When the magma reaches the surface, it erupts. Lava pours across the terrain in flows that can extend for hundreds of kilometers. Dissolved volatile gases, primarily sulfur dioxide, flash out of the magma as pressure drops near the surface, driving explosive eruptions that launch material hundreds of kilometers above the ground in towering plumes. Sulfur compounds are vaporized, lofted, and redeposited across vast areas, painting the surface in vivid yellows and reds and whites. The lava cools, solidifies, and is eventually buried by subsequent flows. The cycle begins again. Orbit drives flexing, flexing drives friction, friction drives heat, heat drives melting, melting drives magma ascent, magma ascent drives eruption. This chain of causation runs continuously, without interruption, powered at every step by the gravitational energy extracted from Io's orbital motion around Jupiter. Io is not powered from inside like Earth. It is being heated from the outside. Jupiter's gravity is the engine. The orbit is the furnace. This distinction between Io's tidal volcanism and Earth's plate tectonic volcanism deserves emphasis because the two systems operate through fundamentally different physical principles, despite producing superficially similar surface expressions. Earth's volcanism, as we have seen, is driven from inside out. Internal heat from radioactive decay and primordial reserves powers mantle convection, which fractures the lithosphere into moving plates, which concentrate volcanic activity along their boundaries. The energy originates within the planet and works its way outward through a chain of thermal and mechanical processes that has been operating for billions of years. On Io, the energy flows in the opposite direction, from outside in. The heat originates not from chemical or nuclear processes within the Moon, but from the mechanical work performed on Io's deformable body by Jupiter's tidal forces as Io traces its eccentric orbit. Gravitational potential energy from the Io-Jupiter orbital system is converted into thermal energy inside Io's mantle through friction. This externally imposed heating does not organize itself into plates or concentrate along boundaries. It deposits energy throughout the mantle broadly and uniformly, producing magma everywhere, which then erupts everywhere, through whatever conduits it can find or create. The result is a volcanic style without terrestrial analogue, hundreds of independently active centers scattered across the surface in no systematic geometric pattern, a world heated from the outside expressing that heat through every available pathway. This distinction also explains why Io's volcanic output so vastly exceeds Earth's despite Io being a far smaller body. Earth's volcanism is throttled by the rate of internal heat production, which depends on the mass of radioactive material and the residual primordial heat, both of which are finite internal resources that deplete over time. Io's volcanism is throttled by the rate of tidal energy dissipation, which depends on orbital parameters, Jupiter's mass, and the rheological properties of Io's interior. The energy source for tidal heating is the gravitational potential energy of the Jupiter-Io orbital system, a reservoir so vast that it can sustain Io's current heat output for billions of years with negligible effect on the orbit. Jupiter is not going to run out of mass. The orbit is not going to run out of energy on any timescale meaningful to planetary geology. The fuel supply is, for all practical purposes, inexhaustible. There is a subtle but important feedback loop operating within this system that determines how efficiently tidal energy is converted into heat. The rheological properties of Io's mantle, its rigidity and viscosity, depend strongly on temperature. A completely solid, cold mantle would be very rigid. It would deform only slightly under tidal stress, and the amount of friction generated would be relatively low. A completely molten mantle would be a fluid. It would deform easily but would flow without significant friction, like stirring water, generating little heat. The maximum tidal dissipation occurs at an intermediate state, where the mantle is partially molten, soft enough to deform substantially under tidal stress but still viscous enough that the deformation generates significant friction. This is precisely the state that Io's mantle appears to occupy. The tidal heating has warmed the interior to the point of extensive partial melting, which coincidentally, or perhaps not coincidentally at all, is the state that maximizes further tidal heating. The system may be self-regulating. If the mantle cools slightly and becomes more rigid, tidal dissipation decreases, allowing the interior to cool further, but the continuing tidal flexing ensures that cooling cannot proceed too far before the mantle returns to the optimal dissipation state. If the mantle overheats and becomes too fluid, dissipation drops as well, allowing it to cool back toward the optimal range. This feedback mechanism may help explain why Io's heat output has remained roughly stable over geological time, rather than fluctuating wildly between extreme states. To appreciate how thoroughly external this energy source is, consider an analogy drawn from everyday experience. Imagine a ball of clay sitting on a table. Left alone, the clay will slowly cool to room temperature and harden. It has no internal energy source to keep itself warm. Now imagine that you pick up the clay and begin kneading it vigorously, squeezing and stretching it, folding it over and pressing it flat, over and over without stopping. The clay heats up. It becomes soft, pliable, warm to the touch. The heat does not come from inside the clay. It comes from your hands, from the mechanical work you are performing on the clay through repeated deformation. If you stop kneading, the clay cools and stiffens again. The warmth persists only as long as the external mechanical input continues. Io is the clay. Jupiter's tidal forces are the hands. The kneading has been ongoing for 4.5 billion years, and it shows no signs of stopping. Every eruption on Io, every plume that arcs above the surface, every lava lake that glows in the infrared night, is the visible surface evidence of this continuous external mechanical heating. Remove the external input and the system winds down. The volcanism does not sustain itself, it is sustained by the orbit. But recognizing that tidal heating is the engine immediately raises a critical follow-up question. Tidal forces do not just heat Io, they also act on its orbit. The same tidal interaction that flexes Io's interior and generates heat simultaneously works to change the shape of Io's orbit. Specifically, tidal dissipation tends to circularize orbits over time. The physics behind this is straightforward. The frictional heating inside Io removes energy from the orbital system. Energy loss causes the orbit to evolve toward a lower energy state, and for an eccentric orbit, the lowest energy configuration at a given angular momentum is a perfect circle. Every calorie of heat generated inside Io by tidal friction represents orbital energy that has been permanently converted to thermal energy and radiated into space. Over time, this energy drain should pull Io's orbit closer and closer to circular. As the orbit circularizes, the variation in tidal force diminishes, the flexing weakens, the heating decreases. Eventually, in a perfectly circular orbit, there is no variation in tidal force at all. The bulge becomes constant, the flexing stops entirely, and the heat production drops to zero. The engine shuts off. This is not a hypothetical scenario. It is what the physics demands. Tidal dissipation drives orbital circularization. Orbital circularization kills tidal heating. Left to itself, the Jupiter-Io tidal interaction would be self-defeating. It would drain the very orbital eccentricity that makes it possible, gradually winding down the volcanic output over millions of years until Io went cold, quiet, and geologically dead. The calculations suggest that without any counteracting force, Io's orbital eccentricity would decay significantly within roughly 100 million years, a long time by human standards, but a small fraction of the solar system's 4.5 billion year history. If nothing were replenishing the eccentricity, Io should have circularized and gone dormant billions of years ago. Yet Io is erupting today as violently as it was when Voyager flew past in 1979. Its orbit is still eccentric, the engine is still running at full power. Something is actively preventing the orbit from circularizing. Something is pumping eccentricity back into Io's orbital path as fast as tidal dissipation drains it away, maintaining the fuel supply for the tidal heating engine against the very forces that would otherwise shut it down. That something is not a single force or a simple interaction. It is a gravitational arrangement of extraordinary precision involving 3 moons locked into an orbital relationship so exact, so stable, and so self-reinforcing that it has functioned as a perpetual energy pump for billions of years. The 2 moons responsible sit just outward from Io in the Jovian system, Europa, the second of Jupiter's 4 large satellites, and Ganymede, the third and largest moon in the entire solar system. Together with Io, they form a gravitational machine called the Laplace resonance, and it is this resonance, this precise clockwork of orbital mechanics, that explains the single most important fact about Io's volcanism. It never stops. Understanding how the resonance works, how 3 moons conspire to keep Io's orbit eccentric against the relentless circularizing pressure of tidal friction, reveals why the most volcanically active body in the solar system is not an accident, not a transient anomaly, not a freakish one-time event. It is an inevitable consequence of orbital architecture, a geological engine that has been running since the moons of Jupiter settled into their current configuration, and that will continue running for as long as the resonance holds. The answer to why Io's eruptions never cease is not in the lava. It is not in the mantle. It is in the orbits of its 2 neighbouring moons. And that is where the story goes next. Jupiter has a staggering number of known moons. As of the most recent confirmed counts, the total exceeds 90. A swarm of captured asteroids, irregular fragments, and icy worldlets orbiting the giant planet at various distances and inclinations. Most of these moons are small, irregularly shaped objects a few kilometers across, too tiny and too distant from Jupiter to play any significant role in the gravitational dynamics of the inner system. But 4 of them are different. 4 of them are worlds in their own right, massive enough to be spherical, large enough to possess complex geology, and influential enough to shape each other's orbital evolution through mutual gravitational interaction over billions of years. These are the Galilean moons, named after the Italian astronomer Galileo Galilei, who first observed them through his small refracting telescope in January of 1610 and recognized that they orbited Jupiter rather than Earth, a discovery that helped dismantle the geocentric model of the universe. In order of increasing distance from Jupiter, the 4 Galilean moons are Io, Europa, Ganymede, and Callisto. Each is a substantial body. Io, as we have already seen, is 3,643 kilometers in diameter, slightly larger than Earth's moon. Europa is slightly smaller, at 3,122 kilometers, but possesses a smooth, ice-covered surface that hides a global saltwater ocean beneath. Ganymede is the largest moon in the entire solar system, 5,268 kilometers across, larger even than the planet Mercury, with its own internally generated magnetic field, the only moon known to possess one. Callisto, the outermost of the 4, measures 4,821 kilometers in diameter and presents an ancient, heavily cratered surface that has remained largely unchanged for billions of years. Together, these 4 moons constitute a miniature planetary system orbiting Jupiter, and the 3 innermost members of this system are connected by an orbital relationship so precise, so mathematically exact, and so consequential for the geology of all 3 worlds that it ranks among the most remarkable dynamical structures in the solar system. The relationship is defined by their orbital periods. Io orbits Jupiter once every 1.769 Earth days, approximately 42 hours and 28 minutes. Europa orbits once every 3.551 Earth days. Ganymede orbits once every 7.155 Earth days. Look at those numbers closely. Europa's orbital period is almost exactly twice Io's. Ganymede's orbital period is almost exactly twice Europa's, and almost exactly 4 times Io's. The ratios are 1 to 2 to 4, with a precision that extends to multiple decimal places. For every single orbit that Ganymede completes around Jupiter, Europa completes precisely 2 orbits, and Io completes precisely 4. This is not an approximate coincidence. It is not a loose clustering of orbital periods that happens to fall near simple integer ratios. It is an exact commensurability maintained by active gravitational coupling between the 3 moons, a dynamical lock that has persisted for an extraordinarily long span of time, and that resists perturbation with remarkable tenacity. This orbital arrangement is called the Laplace resonance, named after the French mathematician and astronomer Pierre-Simon Laplace, who first analysed the dynamics of this 3-body relationship in the late 18th century. Laplace recognised that the integer period ratios were not merely a curiosity of celestial timing, but had profound physical implications for the long-term stability and mutual gravitational interactions of the 3 moons. His mathematical analysis revealed that the resonance was self-maintaining. The gravitational forces exchanged between the moons at specific points in their orbits acted to preserve the period ratios against perturbation, locking the 3 bodies into a stable configuration that could endure for billions of years. To understand how the resonance works and why it matters so critically for Io's volcanism, it helps to visualize the orbital geometry from above. Imagine looking down on the Jupiter system from a vantage point high above the planet's north pole. You see Jupiter at the center, and the 3 moons tracing their elliptical paths around it at different distances and speeds. Io, closest to Jupiter, races around its orbit fastest. Europa, farther out, moves more slowly. Ganymede, farthest of the 3, moves slowest of all. Now watch what happens as time passes. Io, moving faster than Europa, periodically overtakes it on the inside track. The moment when the two moons are closest together, aligned on the same side of Jupiter, is called a conjunction. These Io-Europa conjunctions happen at regular intervals, once for every 2 Io orbits, or equivalently once for every 1 Europa orbit. Critically, because the resonance locks the orbital periods in a precise 2-to-1 ratio, these conjunctions always occur at nearly the same locations in the Moon's orbits relative to Jupiter. The geometry repeats with extraordinary fidelity every time Io laps Europa. The same pattern holds for Europa and Ganymede. Europa overtakes Ganymede periodically, and their conjunctions also occur at specific, repeating orbital locations. And here is the key geometric constraint that defines the Laplace resonance and distinguishes it from simpler two-body resonances. The orbital positions of the Io-Europa conjunctions and the Europa-Ganymede conjunctions are arranged such that all 3 moons are never simultaneously aligned on the same side of Jupiter. When Io and Europa are in conjunction, Ganymede is always on the opposite side of its orbit, roughly 180 degrees away from the other two. When Europa and Ganymede are in conjunction, Io is on the far side of its orbit. The resonance geometrically prevents a triple conjunction from ever occurring. This constraint is not incidental. It is fundamental to the stability of the resonance and to the mechanism by which the resonance pumps energy into Io's orbit. Here is why this matters for Io's volcanism. Every time Io passes close to Europa in their respective orbits, Europa's gravity exerts a small but measurable gravitational tug on Io. This tug is not random. Because the conjunction always occurs at approximately the same orbital position, the direction and timing of Europa's gravitational pull on Io are nearly identical on every pass. This consistency means the effects of the tugs do not cancel out over time. In a system where conjunctions occurred at random orbital positions, the gravitational nudges from Europa would point in different directions each time, and over many orbits, their cumulative effect would average to 0. No net change in Io's orbit would result, but because the resonance fixes the conjunction geometry, the nudges are coherent, they add up. Specifically, they act to pump eccentricity into Io's orbit. Each conjunction gives Io a tiny kick that makes its orbit slightly more elliptical. Individually, each kick is minuscule, but over thousands and millions of orbits, the cumulative effect is substantial. Europa is continuously, systematically feeding eccentricity into Io's orbital path, at a rate that counterbalances the eccentricity being drained away by tidal dissipation. The same dynamical process operates one level outward in the chain. Ganymede's gravitational tugs on Europa, delivered at the fixed conjunction geometry mandated by the resonance, pump eccentricity into Europa's orbit. This keeps Europa's orbit slightly eccentric, which in turn maintains Europa's ability to gravitationally perturb Io at the correct orbital phases. Think of it as a relay. Ganymede, the outermost and most massive of the 3 resonant moons, acts as the anchor. Its gravitational influence on Europa at each conjunction nudges Europa's orbit into a slightly more elliptical shape. Europa, now following a slightly eccentric path, encounters Io at conjunctions with a geometry that systematically kicks Io's orbit away from circularity. Each link in the chain passes the eccentricity-sustaining influence inward, from the most distant resonant moon to the closest. The resonance functions as a linked chain of gravitational forcing. Ganymede drives Europa, Europa drives Io. The eccentricity forcing flows inward through the system, from the outermost resonant moon to the innermost, and the thermal consequences of that forcing ultimately manifest as the tidal heat that powers Io's relentless volcanism. Where does the energy come from originally? It comes from the orbital energy of the system as a whole. The gravitational interactions within the resonance redistribute angular momentum and energy among the 3 moons and Jupiter. Ultimately, the energy that heats Io is extracted from the rotational energy of Jupiter and the orbital energy of the moons. Jupiter is so overwhelmingly massive that the energy drained from its rotation by tidal interaction with the moons is negligible compared to its total rotational energy budget. The fuel supply is, for all practical purposes, limitless on any timescale relevant to planetary geology. The resonance does not need an external energy input to keep running. It recycles the gravitational energy already present in the system, channeling it through a cascade of orbital interactions that terminate in the frictional heating of Io's interior. The stability of the Laplace resonance is one of its most remarkable properties. Orbital resonances can be either stable or unstable, depending on the specific geometry and the masses involved. An unstable resonance would amplify any small perturbation, causing the orbital ratios to drift apart until the resonance breaks. A stable resonance does the opposite. Small perturbations are corrected by the gravitational forces within the resonance itself, pulling the system back toward the exact integer ratios. The Laplace resonance is stable. If some external influence were to slightly increase Io's orbital period, pushing it away from the exact 4:1 ratio with Ganymede, the resulting change in conjunction geometry would alter the gravitational kicks in a way that restored the original period. The resonance acts as a self-correcting mechanism, maintaining the orbital lock against perturbation. This is why it has survived for such an enormous span of time. Estimates of the resonance's age vary, but most analyses suggest it has been operating for a substantial fraction of the solar system's 4.5 billion year history. Some models propose that the resonance assembled gradually as tidal interactions between Jupiter and its moons caused the moon's orbits to migrate outward at different rates, eventually sweeping them into the resonant configuration. Once established, the resonance locked in and has been running continuously ever since. Other models suggest the resonance may have formed very early in the history of the Jovian system, during or shortly after the formation of the moons from the circumjovian disk of gas and dust. Regardless of its precise origin, the resonance has been operational for long enough to sustain Io's current volcanic output for billions of years. The self-correcting stability of the resonance also means it is robust against the very process it enables. Tidal dissipation inside Io removes energy from the system. In a non-resonant configuration, this energy loss would cause Io's orbit to evolve, spiraling the moon inward toward Jupiter over time. But within the resonance, the orbital evolution of all three moons is coupled. Energy lost to tidal heating in Io is compensated by adjustments in the orbits of all three resonant moons, mediated by their gravitational interactions. The system evolves as a unit, maintaining the resonant ratios even as energy is dissipated. The resonance does not fight against tidal heating. It accommodates it, redistributing the consequences of energy loss across the entire three-moon system so that no single moon's orbit is catastrophically altered. This coupling is what allows the resonance to persist despite the enormous rate of tidal energy dissipation occurring within Io. The system adjusts, adapts, and continues running. To fully appreciate the significance of the Laplace resonance for Io, it is essential to understand what would happen if the resonance were to break. Suppose, through some hypothetical mechanism, a catastrophic external perturbation, perhaps the gravitational influence of a rogue body passing through the Jupiter system, disrupted the precise 1 to 2 to 4 orbital period ratios. Io, Europa, and Ganymede would no longer be locked in their resonant configuration. The conjunctions between pairs of moons would begin occurring at different orbital positions each time, rather than at fixed repeating locations. The gravitational nudges exchanged during these conjunctions would lose their coherence. Sometimes Europa would tug Io in a direction that increased its eccentricity. Other times, the tug would decrease it. Over many orbits, the effects would average towards zero. The systematic pumping of eccentricity into Io's orbit would cease. Without the resonance replenishing it, Io's orbital eccentricity would begin to decay under the relentless circularizing influence of tidal interaction with Jupiter. The physics is straightforward. Tidal dissipation removes energy from the orbit, and for an eccentric orbit, the natural evolution under energy loss is towards circularity. The timescale for this circularization is not precisely known, because it depends on the detailed rheological properties of Io's interior, which are themselves uncertain. but most estimates suggest that significant eccentricity decay would occur within roughly 100 million years, and near-complete circularization might be achieved within a few 100 million years. These are long timescales by human standards, but geologically brief compared to the age of the solar system. As the eccentricity declined, the consequences for Io's volcanism would be direct and devastating. Recall the chain of causation established earlier. Orbital eccentricity drives varying tidal forces. Varying tidal forces drive cyclic interior flexing. Cyclic flexing drives frictional heating. Frictional heating drives mantle melting. Mantle melting drives magma ascent and surface eruption. Remove the eccentricity, and you remove the first link in the chain. Everything downstream collapses. The tidal bulge would become increasingly constant as the orbit approached circularity. The cyclic flexing would weaken. The amplitude of the compression and release cycle would diminish. Internal friction would decrease. Heat production would fall. The decline would not be instantaneous. Io's interior has enormous thermal inertia, meaning it takes a long time for a body that large to cool, even after its heat source diminishes. The mantle would remain hot, and volcanism would continue for millions of years after the eccentricity began decaying, but at a gradually declining intensity. Eruptions would become less frequent. Plumes would not reach the same heights. Lava flows would shorten and thin. The magma ocean, or extensive partial melt zone, thought to exist beneath Io's crust, would begin to solidify from the outside in, as heat loss through the surface exceeded the diminishing heat input from tidal flexing. Over tens of millions of years, the transition would become visible on the surface. Regions that had been continuously active would fall silent one by one as the underlying magma supply cooled and solidified. The great lava lakes would crust over permanently, their periodic overturning cycles lengthening and then ceasing altogether as the magma beneath thickened and stiffened beyond the point where crustal foundering could occur. Plumes that had risen for decades or centuries would weaken, their fountains dropping lower, their canopies thinning, until the last jets of sulfur dioxide sputtered into the vacuum and stopped. The rate of volcanic resurfacing would slow. For the first time in billions of years, impact craters would begin to accumulate on Io's surface, no longer being buried faster than they formed. The vivid sulfurous colours would gradually fade under the bombardment of charged particles from Jupiter's intense radiation belts, a process called space weathering that currently has no chance to alter Io's appearance because fresh volcanic deposits continuously bury the weathered surface. Without that constant renewal, the radiation would slowly break down the sulfur compounds, darkening and greying the once vivid palette. The yellows and reds would dull, the surface would darken. The world that had blazed with infrared light visible from Earth-based telescopes would dim, its thermal signature fading to match the cold background of every other small inert body in the outer solar system. Over a few 100 million years, Io would transform from the most volcanically active body in the solar system into something resembling its outermost sibling, Callisto, a cold, cratered, geologically inert sphere of rock and ice. Its explosive past preserved only in the chemical signatures of its interior, and the lingering remnants of once molten structures buried deep beneath an increasingly ancient surface. This counterfactual scenario is not merely a thought experiment. It is a direct test of the causal argument at the heart of the entire story. If the resonance is truly the mechanism that sustains Io's volcanism, then removing the resonance should kill the volcanism. And the physics says it would, unambiguously. The chain of causation runs from resonance to eccentricity to tidal flexing to frictional heat to magma to eruption. Break the first link, and every subsequent link fails. The counterfactual confirms the causal model. Io's volcanism is not self-sustaining. It is not powered by any process internal to the Moon that would continue operating regardless of orbital configuration. It is entirely dependent on the external gravitational architecture that maintains its orbital eccentricity, and that architecture is the Laplace resonance. The contrast between Io and Callisto makes this point with striking clarity. Callisto, the outermost Galilean moon, orbits Jupiter at a distance of roughly 1,883,000 kilometers, more than 4 times farther out than Io. It is not part of the Laplace resonance. Its orbit is not significantly perturbed by the other Galilean moons. It experiences tidal forces from Jupiter, but because it is so much farther away and because its orbit has very low eccentricity, the tidal heating is negligible. The result is visible on its surface. Callisto is one of the most heavily cratered objects in the solar system. Its surface has remained essentially unchanged for billions of years, a museum of ancient bombardment preserved in ice and rock. There is no evidence of recent geological activity of any kind. No volcanic flows, no tectonic fractures, no resurfaced plains. Callisto is what Io would look like if the resonance did not exist. 2 moons of similar size, orbiting the same planet, in the same region of the solar system, yet one is a volcanic furnace and the other is a frozen relic. The only fundamental difference between them is their orbital dynamics. Io is locked in a resonance that forces eccentricity and drives tidal heating. Callisto is not. The geology follows from the orbit. The orbit is the furnace, and the resonance is the reason the furnace stays lit. The resonance also illuminates something important about the nature of the energy flow powering Io's eruptions. In everyday experience, we tend to think of heat as something generated locally. A fire burns because fuel and oxygen react at the location of the flame. A light bulb glows because electrical resistance heats the filament inside the glass envelope. A person feels warm because metabolic reactions produce heat within their body. These are all examples of local energy conversion, where the source of heat and the location of heating are the same. Io's tidal heating operates on a completely different principle. The energy source is the gravitational interaction between 3 moons and a giant planet, spread across a volume of space, millions of kilometers in extent. The energy conversion occurs inside Io's mantle, hundreds or thousands of kilometers below the surface. The visible expression of that energy, the eruptions and plumes and lava flows, occurs on the surface. The source, the conversion site, and the expression are all in different locations, connected by chains of physical causation that span enormous distances and operate through gravitational, mechanical, and thermal processes in sequence. This is energy teleportation through orbital mechanics. Gravitational potential energy residing in the configuration of 3 distant moons and a giant planet is converted into thermal energy inside the mantle of one specific moon, not through any direct physical contact, but through the invisible medium of gravitational tidal forces acting across hundreds of thousands of kilometers of empty space. The Laplace resonance has implications that extend beyond Io to the other moons participating in the resonant chain. Europa, the second moon in the sequence, also maintains a forced orbital eccentricity sustained by gravitational interactions with Ganymede on the outside and Io on the inside. Europa's eccentricity is smaller than Io's, and its greater distance from Jupiter means weaker tidal forces, so the tidal heating rate in Europa is significantly lower than in Io, but it is not zero. Current estimates suggest that Europa's tidal heat production is sufficient to maintain a global ocean of liquid water beneath the moon's icy shell, an ocean that may contain roughly 2 to 3 times the volume of all liquid water on Earth. The implications of this subsurface ocean for the search for extraterrestrial life are profound, and we will return to them shortly. For now, the critical point is that the same orbital machine that turns Io into a volcanic hellscape is simultaneously maintaining a liquid water environment on the next moon outward, sustained not by sunlight or internal heat, but by the gravitational clockwork of the resonance itself. Ganymede, the outermost member of the resonance, experiences the least tidal heating of the 3 because it orbits farthest from Jupiter and has the smallest forced eccentricity. Nevertheless, Ganymede shows evidence of past geological activity in the form of grooved terrain, regions of relatively young, tectonically deformed surface that contrasts sharply with the ancient, heavily cratered dark terrain that covers the rest of the moon. Some researchers attribute this past geological activity to periods of enhanced tidal heating that may have occurred as the resonance evolved and the orbital parameters shifted over billions of years. Ganymede's internally generated magnetic field, unique among all moons in the solar system, may also be connected to residual or ongoing heat sources in its deep interior, potentially including a contribution from tidal dissipation. The gradient of geological activity across the three resonant moons, intense on Io, moderate on Europa, mild on Ganymede, correlates precisely with the expected gradient of tidal heating intensity, which decreases sharply with distance from Jupiter. And the fourth Galilean moon, Callisto, which sits outside the resonance entirely, shows no geological activity at all. This gradient is perhaps the most powerful single piece of evidence supporting the tidal heating model. 4 moons of broadly similar size and composition, orbiting the same planet in the same region of the solar system. 3 are in a resonance, 1 is not. The 3 resonant moons show geological activity proportional to their expected tidal heating rates. The non-resonant moon is dead. The pattern could hardly be more clear or more diagnostic. Jupiter's gravity is the engine that heats Io. The orbital eccentricity is the variable that allows the engine to operate. And the Laplace resonance is the mechanism that maintains the eccentricity against the very forces that would otherwise erase it. Without the resonance, the eccentricity would decay, the tidal flexing would cease, the heating would stop, and Io would go cold. With the resonance in place, the eccentricity is continuously replenished. The flexing continues without pause, the heat pours in, and the eruptions never stop. The resonance is the lock that keeps the engine running. It is the reason that Io has been volcanically active for billions of years and will continue to be volcanically active for billions of years to come, as long as the 3 moons remain in their precise orbital dance around the most massive planet in our solar system. We have now traced the complete causal chain from beginning to end. Resonance sustains eccentricity. Eccentricity enables flexing. Flexing generates heat. Heat produces magma. Magma drives eruption. Every link is grounded in well-understood physics, and every prediction this model makes about Io's behavior matches the observations. No link in the chain is speculative. No step requires unknown physics or exotic energy sources. The mathematics of orbital mechanics, the thermodynamics of viscoelastic dissipation, and the fluid dynamics of magma transport are all established disciplines with decades of theoretical and experimental support. What makes Io extraordinary is not that it requires new science to explain. It is that familiar, well-tested science produces such an extreme outcome when the orbital parameters align. The resonance is the reason. The orbit is the furnace. And what remains is to look more closely at what this orbital furnace actually produces on the surface of the world it torments, to see what the eruptions look like when you examine them in detail, and to understand what this extraordinary moon teaches us about how the universe builds worlds, not through internal fire, but through the patient, relentless, invisible hand of gravity operating across empty space. If you could survive the radiation, endure the temperature extremes, and somehow plant your boots on the surface of Io, the world you would encounter would look like nothing else in human experience. No photograph transmitted from spacecraft across hundreds of millions of kilometers of space fully conveys what it would mean to stand on this ground and look around. The terrain beneath your feet would be a fractured, layered crust of sulfurous compounds and solidified lava. The vivid colors described earlier, visible not as patterns on a distant photograph, but as the actual ground stretching to every horizon. The textures vary enormously. In some regions, the surface is smooth and glassy, freshly paved by recent flows that solidified in the vacuum only months or years ago. In others, it is rough, crumbling, and stratified, each layer representing a different eruption cycle deposited on top of the last. Mountains tower in the middle distance, not volcanic cones, but enormous fractured massifs of crustal rock thrust upward by tectonic compression, as buried material is slowly forced back into the interior beneath the weight of accumulating volcanic deposits. Some of these mountains exceed 15 kilometers in height, taller than anything on Earth, their cliffs sheer and angular because no wind or water erosion exists to soften their profiles. In every direction, the horizon is closer than you would expect, a consequence of Io's small diameter curving the surface away beneath you more sharply than Earth's does. The landscape feels compressed, foreshortened, as though the world drops away too quickly at the edges. There is no sound. Io's near-vacuum atmosphere transmits nothing. An eruption could be occurring just beyond the horizon, launching debris hundreds of kilometers overhead, and you would experience it in total silence. The radiation is invisible but overwhelming. Jupiter's powerful magnetosphere accelerates charged particles to enormous energies, and Io sits deep within the most intense radiation belt, bathed in a constant flux that would incapacitate unshielded electronics and biological tissue alike within minutes of exposure. This is not a place that tolerates visitors. Overhead, the sky is essentially black. Io possesses an atmosphere so thin, roughly 1 billion times less dense than Earth's at sea level, that it provides no blue scattering, no weather, no clouds in any conventional sense. Jupiter dominates the sky above, an immense banded disk spanning roughly 20 degrees of arc, nearly 40 times the apparent width of the full moon seen from Earth. Its cloud bands and storm systems visible in exquisite detail, a permanent fixture in Io's heavens that never rises and never sets because Io is tidally locked, always presenting the same hemisphere toward the giant planet. The volcanic plumes that define Io's character come in 2 broadly distinct varieties, each driven by different mechanisms and producing different surface signatures. The first type is exemplified by the volcano Prometheus, one of the most persistently active features on Io's entire surface. Prometheus-type plumes are relatively modest in height, rising to altitudes of roughly 50 to 100 kilometers above the surface. They are sustained eruptions, persisting for months, years, or even decades with remarkable steadiness. The mechanism driving them is elegant in its simplicity. Prometheus and similar volcanoes produce active silicate lava flows that advance slowly across the surrounding terrain. As these flows creep forward over ground coated in sulfur dioxide frost, the intense heat of the molten rock vaporizes the frost ahead of and beneath the flow front. The sulfur dioxide transitions from solid frost directly to expanding gas, generating a continuous fountain of vapor and entrained fine particles that rises above the advancing lava front in a steady, relatively gentle plume. The process is self-sustaining as long as the lava flow continues advancing over fresh frost-covered ground. When Voyager first imaged Prometheus in 1979, the plume was active. When Galileo arrived 16 years later, the plume was still active, though the source vent had migrated roughly 80 kilometers from its original position. Carried along by the advancing front of the underlying lava flow, Prometheus has been erupting, without any confirmed interruption, for more than 4 decades of human observation. The deposits from Prometheus-type plumes form characteristic bright rings of fresh sulfur dioxide frost surrounding the active vent, visible from orbit as circular or elliptical halos that can span hundreds of kilometers in diameter. The second type of plume is far more violent and far more spectacular. These are the Pele-type eruptions, named after the volcanic center Pele, one of the first and most dramatic plume sources identified by Voyager. Pele-type plumes are driven not by lava-frost interaction, but by the direct explosive outgassing of deep volcanic vents tapping large magma reservoirs. The gases involved, primarily sulfur dioxide with significant contributions from elemental sulfur vapor and other volcanic volatiles, erupt from the vent at velocities approaching or exceeding 1 kilometer per second. This is faster than a rifle bullet. The material is launched essentially into vacuum because Io's negligible atmosphere provides no resistance whatsoever to the expanding gas and debris. In Io's weak gravitational field, roughly 1/5 the strength of Earth's surface gravity, these high-velocity eruptions achieve extraordinary heights. Pele-type plumes routinely reach 300 to 500 kilometers above the surface. The Tvashtar eruption imaged by New Horizons in 2007 produced a plume approximately 330 kilometers tall, and there are indications from earlier observations that some eruptions may have reached even greater altitudes during their most energetic phases. The material ejected in these plumes follows ballistic trajectories, arcing outward from the vent in a vast umbrella-shaped canopy that spreads debris across areas comparable in size to large European nations. The deposits from Pele-type eruptions are visually distinctive. Vivid red and dark rings of sulfur and silicate particles that contrast sharply with the surrounding yellow and white terrain, creating bullseye-like patterns visible from millions of kilometers away. The difference in scale between these two plume types reflects differences in the underlying volcanic processes, but both are ultimately expressions of the same tidal heat engine operating beneath the surface. Prometheus-type plumes represent the shallow end of the system, where tidally driven lava effusion encounters surface volatile deposits and vaporizes them into sustained fountains. The magma feeding these flows originates in the tidally heated mantle, rises through the crust along established conduits, and spreads laterally across the surface. The plume itself is a secondary effect of the flow's advance over frost-covered ground. Pele-type plumes represent the deep end of the system, where large reservoirs of tidally heated magma accumulate beneath the crust under pressure, trapping dissolved volcanic gases until the pressure exceeds the strength of the overlying rock and the system ruptures explosively. These are eruptions powered directly by the volatile content of deep magma, rather than by surface frost interaction. Both trace their energy back through the same causal chain. Resonance maintains eccentricity. Eccentricity enables tidal flexing. Flexing generates frictional heat. Heat produces magma, and magma drives eruption. The surface diversity of Io's volcanic expressions emerges from a single underlying mechanism expressed through different pathways and different interactions with surface materials. Among the most intensively studied individual features on Io is Loki Patera, a volcanic depression located in Io's northern hemisphere that contains the most powerful, persistently active lava lake known anywhere in the solar system. Loki Patera is not a conventional volcanic crater in the terrestrial sense. It is an enormous caldera-like depression, roughly 200 kilometers across, partially filled with an active body of molten silicate lava. The surface of this lava lake is covered by a thin, dark crust of solidified rock that forms as the exposed magma radiates heat into space and cools. This crust is unstable. Periodically, sections of the crust become dense enough to founder, sinking back into the underlying liquid magma like ice breaking up on a warming pond. When the crust founders, fresh, incandescent magma is exposed at the surface, and the thermal output of the entire feature increases dramatically, producing brightening events that are detectable from Earth using ground-based infrared telescopes. These overturning events propagate across the lake surface in a wave, advancing at a rate of roughly 1 to 2 kilometers per day, taking months to traverse the full extent of the feature before a new crust stabilizes and the cycle begins again. The periodicity of Loki's brightening events is approximately 400 to 540 days, though the interval varies and the process is not perfectly clock-like. What is remarkable about Loki Patera is not merely its size or its persistence, but its thermal output. This single volcanic feature, one depression on one moon, radiates more heat than all of Earth's active volcanoes combined. One lava lake, on a moon smaller than our own, outperforms the entire volcanic heat output of a planet 67 times more massive. That comparison, perhaps more than any other single fact, encapsulates the extraordinary nature of tidally driven volcanism. The overall pattern of volcanic activity on Io's surface reveals something fundamental about how tidal heat is distributed and released within the moon. On Earth, volcanic activity concentrates along linear features, mid-ocean ridges, subduction zone arcs, and transform boundaries. This linear distribution reflects the plate tectonic framework that organizes and channels Earth's internal heat release. Io displays no such organization. Its volcanic centers are distributed broadly across the surface, concentrated somewhat in the equatorial and mid-latitude regions, where tidal heating models predict dissipation rates should be highest, but without the linear geometric patterns characteristic of plate boundaries. There are no ridges, no trenches, no systematic arcs of volcanoes following the edges of interacting crustal blocks. The volcanic output is dispersed uniformly across the globe, reflecting a heat source that is deposited throughout the mantle volumetrically, rather than being focused along narrow boundary zones. Planetary scientists describe the process by which Io releases this globally distributed heat as heat pipe volcanism. The term captures a mechanism fundamentally different from plate tectonic recycling. In a heat pipe regime, magma generated throughout the mantle rises vertically through the lithosphere along numerous independent conduits, erupts on the surface, and deposits lava that builds up the crust from above. As new lava accumulates on top of older flows, the older material is buried, compressed under the growing weight of overlying deposits, and gradually pushed downward back into the interior, where it is reheated by continuing tidal dissipation and eventually remelted to complete the cycle. The entire crust is being continuously built up from above and recycled downward from below, not through the lateral sliding of plates over a convecting mantle, but through vertical transport of material in a process more analogous to a conveyor belt running perpendicular to the surface rather than parallel to it. This vertical recycling is efficient at transporting heat from the interior to the surface, which is why Io's heat flux is so extraordinarily high despite the Moon's small size. The heat does not need to wait for slow mantle convection to carry it laterally to plate boundaries. It punches straight up through the lithosphere along hundreds of volcanic conduits and escapes directly into space as radiated thermal energy from lava flows and volcanic deposits. This heat pipe mechanism is not merely an exotic curiosity specific to Io. It may represent a volcanic regime that operated on early Earth and other terrestrial planets during their youngest, hottest geological epochs, when internal heat production from residual accretional energy and the decay of long-lived radioactive isotopes was far higher than it is today. During Earth's Hadean eon, more than 4 billion years ago, our planet's interior was significantly hotter. Plate tectonics may not yet have been established in its modern form, and volcanic activity was far more intense and globally distributed than it is now. Some geophysicists have proposed that early Earth operated in a heat pipe mode similar to Io's current state, with vigorous vertical magma transport dominating over organized lateral plate motion. Under such a regime, overlapping lava flows would have paved and repaved the surface relentlessly, building up thick volcanic crusts that were continuously buried and recycled downward under the weight of fresh eruptions, precisely the process observed on Io today. Ultramafic magmas, similar to the komatiites discussed earlier, may have erupted frequently across the young Earth's surface, driven by mantle temperatures high enough to produce the same primitive, magnesium-rich lavas that Io still generates. If this hypothesis is correct, then Io provides a living laboratory for studying a volcanic regime that Earth passed through billions of years ago, but that left only fragmentary evidence in the oldest surviving terrestrial rocks. The Hadean is the most poorly preserved chapter of our planet's history, its record almost entirely erased by 4 billion years of subsequent geological activity. Observing Io today may be, in a very real sense, like looking at a snapshot of Earth's deep geological past preserved on another world. Everything observed on Io's surface, every plume, every lava lake, every sulfurous plain, every dark silicate flow, connects back through an unbroken chain of physical causation to the orbital resonance that maintains the tidal heating engine. Io is not powered from inside like Earth. It is being heated from the outside by the gravitational energy of a 3-moon resonance channeled through the tidal forces of the largest planet in the solar system. The surface violence is the terminal expression of orbital mechanics operating with the regularity and predictability of a mathematical theorem. There is no mystery in Io's volcanism once you understand the resonance. There is only physics. The significance of what Io teaches us extends far beyond the Jupiter system and far beyond the study of volcanism. Io was the proof of concept that changed how planetary scientists think about geological energy sources throughout the universe. Before 1979, the working assumption across the field was that a world needed to be large, young, or close to a star to be geologically active. Size provided the thermal inertia to retain primordial heat. Youth meant radioactive isotopes had not yet decayed to insignificance. Proximity to a star provided external energy in the form of solar radiation that could drive atmospheric and surface processes, though not volcanism directly. A small, old, cold moon orbiting in the distant outer solar system, more than 5 times farther from the Sun than Earth, was supposed to be dead. Io obliterated that assumption. Here was a world that satisfied none of the traditional criteria for geological activity, yet erupted with a fury that surpassed every planet in the inner solar system. The energy source was entirely novel in the context of observed solar system geology. Gravitational tidal heating, sustained by orbital resonance, powered by the orbital mechanics of a multi-moon system around a giant planet. The discovery opened an entirely new category of geological energy source, one that depends not on the internal properties of a world, but on its orbital environment. The implications cascaded outward immediately to the other moons in the Jovian system. Europa, the second moon in the Laplace resonance, became one of the most compelling targets in the entire solar system for the search for extraterrestrial life, and it became so specifically because of what Io demonstrated about tidal heating. Europa's forced orbital eccentricity, maintained by the same resonance that drives Io's volcanism, produces tidal heating within Europa's interior at a lower but still significant rate. This heat is believed to be sufficient to maintain a global ocean of liquid salt water beneath Europa's icy shell, an ocean that may contain roughly 2 to 3 times the volume of all liquid water on Earth. The existence of this ocean is supported by multiple independent lines of evidence. The Moon's induced magnetic field signature detected by Galileo, which is consistent with a conductive fluid layer beneath the ice. The young, sparsely cratered, and tectonically disrupted appearance of Europa's surface, indicating recent geological activity, and the detection by the Hubble Space Telescope of possible water vapor plumes erupting from the Moon's south polar region, suggesting that subsurface liquid is occasionally vented into space. If Europa's ocean is in contact with a rocky seafloor, as most models suggest, then the combination of liquid water, dissolved minerals from water-rock interactions, and a sustained energy input from tidal heating creates conditions that parallel those found at hydrothermal vent systems in Earth's deep oceans. On Earth, hydrothermal vents support thriving ecosystems of chemosynthetic organisms, bacteria, tube worms, shrimp, and other life forms that derive their energy not from sunlight, but from chemical reactions between hot, mineral-laden vent fluids and cold seawater. These ecosystems demonstrate that life can persist in total darkness, at crushing pressures, and at extreme temperatures, sustained entirely by geochemical energy. If analogous vent systems exist on Europa's seafloor, they could potentially support microbial life or even more complex organisms. None of this would be considered plausible if Io had not first demonstrated that tidal heating is a real, powerful, and sustained energy source capable of driving geological processes on small, cold moons far from the Sun. The principle extends to the Saturn system as well. Enceladus, a tiny moon only about 504 kilometers in diameter, roughly 7 times smaller than Io, was discovered by the Cassini spacecraft to be actively venting plumes of water ice, water vapor, and organic molecules from fractures near its south pole. These plumes originate from a subsurface ocean of liquid water maintained, like Europa's, by tidal heating. Enceladus participates in a 2-to-1 orbital resonance with the larger Saturnian moon Dione, and this resonance maintains the orbital eccentricity that enables tidal heating within Enceladus despite the moon's diminutive size. The Cassini spacecraft flew directly through Enceladus's plumes on multiple occasions, threading a path that carried the spacecraft within 50 kilometers of the moon's surface, at speeds exceeding 8 kilometers per second. On each pass, Cassini's instruments sampled the plume material in real time, its ion and neutral mass spectrometer and cosmic dust analyzer, capturing and identifying individual molecules and ice grains ejected from the fractures below. The composition data returned from these fly-throughs revealed not only water and simple organic compounds but also molecular hydrogen, a finding published in 2017 that provided some of the strongest evidence yet for active hydrothermal chemistry on another world's seafloor. Scientists had hypothesized that such reactions might be occurring beneath Enceladus's ice, but detecting the chemical signature directly in the plume material confirmed that hot water and rock were interacting at the bottom of an alien ocean in the present day. The detection of molecular hydrogen was particularly significant because on Earth, hydrogen produced by hydrothermal reactions serves as an energy source for methanogenic microorganisms, simple life forms that metabolize hydrogen and carbon dioxide to produce methane. The chemistry required for at least the simplest forms of life may already be present on Enceladus, powered by the same fundamental mechanism that Io first revealed to science: tidal energy, sustained by orbital resonance, converting gravitational potential into geological heat inside a world that has no business being geologically active by any traditional criterion. The implications stretch still further, beyond our solar system entirely, into the realm of exoplanetary science and the search for habitable environments throughout the galaxy. Astronomers have now confirmed the existence of thousands of exoplanets, and a significant fraction of these are gas giants orbiting at various distances from their host stars. These giant planets almost certainly possess moons, just as Jupiter and Saturn do in our own system. We cannot yet detect exomoons directly with current technology, but their existence is statistically near certain given the universality of the moon formation processes observed in our solar system. If even a small fraction of these exomoons are locked into orbital resonances analogous to the Laplace resonance, they could experience tidal heating sufficient to maintain liquid water oceans, drive geological activity, and potentially sustain habitable environments, regardless of their distance from the parent star. A moon orbiting a gas giant in the cold outer reaches of a distant planetary system, far beyond the conventional habitable zone where stellar radiation can maintain surface liquid water, could nonetheless possess a warm, chemically active subsurface ocean powered entirely by tidal energy. Habitability, in other words, is not limited to the narrow ring around a star where temperatures permit liquid water on a surface exposed to space. It can exist deep inside icy shells, in darkness, sustained by the invisible hand of gravitational orbital mechanics, anywhere in the galaxy where the right orbital architecture exists. Io was the discovery that first opened this door. Every subsequent detection of tidal activity on Europa, on Enceladus, on any other world, traces its intellectual lineage back to the moment Linda Morabito noticed a bright arc extending off the limb of a small Jovian moon in a navigation photograph. There is a deeper lesson embedded in Io's story that extends beyond geology and planetary science into the realm of how we understand the relationship between violence and stability, between chaos and order, in physical systems. Io's surface is among the most geologically violent environments known to exist. Lava buries everything. 100-kilometer plumes blast debris into space. Sulfurous compounds rain from the sky. The radiation environment created by Jupiter's magnetosphere bombards the surface with energetic charged particles at dose rates lethal to any known organism within minutes. By every intuitive measure, Io is a world defined by destruction, impermanence, and relentless upheaval. Yet the engine that produces this surface chaos is one of the most stable and orderly dynamical configurations in the solar system. The Laplace resonance is a precision gravitational clock. 3 moons trace their orbits in exact integer ratios, exchanging angular momentum and energy through gravitational interactions that repeat with mathematical fidelity on every orbital cycle. The resonance is self-correcting, self-sustaining, and resistant to perturbation. It has operated for billions of years and will continue operating for billions more. The most violent surface in the solar system is produced by one of the most stable and elegant mechanisms in orbital mechanics. Disorder at the surface, perfect order in the orbit. The chaos is not random. It is the predictable, inevitable, mathematically determined output of a system operating exactly as physics demands. This relationship between orbital order and surface violence teaches something profound about how the universe constructs extreme phenomena. Io's eruptions are not the result of catastrophe, instability, or breakdown. They are the result of a system functioning precisely as designed by the laws of gravity and motion. The violence is not a sign that something has gone wrong. It is a sign that everything is working exactly as it must. The resonance feeds eccentricity into Io's orbit. The eccentricity enables tidal flexing. The flexing generates heat. The heat drives eruption. Every step follows from the previous one with the inevitability of a mathematical proof. The conclusion, the volcanic fury that makes Io the most explosive world in the solar system, is not surprising once you understand the premises. It is compulsory. Given the masses involved, the orbital distances, and the resonant period ratios, Io's volcanism is not just possible, it is unavoidable. This is perhaps the most important insight that Io offers to anyone trying to understand the natural world. The most extreme phenomena in the universe are not always the products of extreme accidents. Sometimes they are the products of ordinary physical laws operating in extraordinary configurations. Gravity is the most familiar force in human experience. Every child who drops a ball understands gravity intuitively. Orbital motion is simple enough that Kepler described its laws 4 centuries ago with nothing more than careful observation and geometry. Resonance is a concept familiar to anyone who has pushed a child on a swing, delivering small pushes at the right moment to build enormous amplitude. These are not exotic principles. They are the most basic elements of classical mechanics. Yet when these ordinary principles combine in the specific configuration present in the Jovian system, they produce a world where the ground is literally being torn open by forces originating hundreds of thousands of kilometers away in empty space, where lava hotter than anything erupted on Earth in 2 billion years pours across a surface painted in alien chemistry, where volcanic plumes reach heights that would carry them into low Earth orbit if they occurred on our planet. Ordinary physics, extraordinary outcome, that is the lesson of Io. Io is not a mystery. It is not an anomaly that defies the laws of nature. It is not a world tearing itself apart in some catastrophic, unsustainable paroxysm. It is a world in dynamic equilibrium. The energy flowing in through tidal dissipation roughly equals the energy flowing out through volcanic radiation. The interior is not spiraling toward collapse. It is maintaining itself in a steady state, heated from the outside by gravitational forces and cooled from the surface by thermal radiation into space. The balance has held for billions of years. It will hold for billions more. The eruptions are not symptoms of crisis. They are symptoms of stability, the visible evidence that a well-tuned gravitational machine is operating exactly as the laws of physics require. The next time you look at Jupiter in the night sky, visible as a bright, steady point of light in the constellation it happens to be transiting, know that just beside it, far too small and too close to the giant planet's glare to see with your unaided eyes, there is a moon being reshaped in real time by forces that originate not within its own body, but in the gravitational architecture of the system it inhabits. Its interior flexes on every orbit. Its mantle churns with magma sustained by friction it did not generate internally. Its surface remakes itself faster than human civilizations rise and fall, burying everything older under fresh deposits of lava and sulfurous frost. Plumes of gas and debris arc hundreds of kilometers into the black sky and fall back as colored snow. Lava lakes overturn in slow, planet-shaming pulses of thermal energy, all of it driven by the same force that holds your feet to the ground and the moon in orbit around the Earth. Gravity, the simplest, weakest, most familiar force in nature, but channeled through resonance, focused through orbital eccentricity, and amplified by the colossal mass of the largest planet in the solar system, gravity becomes something else entirely. It becomes a geological engine capable of turning a small, cold, ancient moon into the most volcanically active world we have ever found. Io is not magic. It is not a miracle of exotic physics or unknown energy sources. It is orbital mechanics made violent. A world forced into permanent eruption by the geometry of its path around Jupiter and the gravitational rhythm it shares with two sibling moons. The most explosive world in the solar system, powered by nothing more than the patient, invisible, mathematically precise pull of gravity operating across empty space. The eruptions are not the mystery. They are the answer, the visible surface expression of a stable orbital energy machine, a world held in the grip of resonance and gravity, erupting not because something has broken, but because everything is working exactly as physics demands. That is Io. That is what gravity can do to a world. And now that you understand the mechanism, you will never look at a moon the same way again.